Welcome to this deep dive into foundational concepts brought to you by CBSE ScoreLab of ProfSam.com, that is ProfSam.com. Today we are undertaking a deep dive into the concept of transformers from Unit 7, Alternating Current. Our mission is to understand this essential device so intuitively that you not only master the formulas but also understand why the entire modern electrical world depends on it. Okay, let's unpack this with a simple observation. Have you ever stood near one of those, green or gray electrical boxes or maybe a large substation and noticed that specific, low, deep humming sound? It is a constant, almost musical sound, and yet there are no obvious moving parts inside.
Yes, I know exactly the hum you mean. It is strangely powerful, and what strikes me is the incredible energy transfer that must be happening right there. They must be managing enormous changes in electricity levels.
They are, and that's the core of the mystery. Think about the sheer scale of the operation. Those enormous transmission lines bring in power at extreme voltages, maybe 11,000 volts or even hundreds of thousands of volts. The substation then takes that power and steps it down drastically to the 230 volts we need for our homes.
And that's just the big picture. When I charge my laptop or my phone, my little wall adapter takes that 230 volts and drops it even further, sometimes down to just 5 volts. The difference between 200 and 5 is massive, and it happens silently in a classic box.
Exactly. How is this colossal, dramatic change in voltage levels achieved so efficiently, safely, and economically, all without a single piston or gear turning? This efficiency and flexibility is the entire genius of the transformer. It is the device that solved one of the biggest infrastructure problems in history, allowing us to use alternating current everywhere. So let's jump straight to the fundamental idea at a zero level. What is this device?
The transformer is a a non-moving apparatus designed to change AC voltage from one value to another, either stepping it up or stepping it down. Crucially, its operation is based purely on the principle of mutual induction, which, relies on a constantly changing magnetic field. And since energy must be conserved, there is a fundamental trade-off we must internalize. If the voltage goes UP, the current must come down proportionally, and vice versa.
So if the voltage doubles, the current must have, assuming no energy losses. We are only changing the configuration of the energy, not the total power. Precisely. We are just changing the ratio of voltage to current. And that seemingly simple exchange is the only reason alternating current won the current wars over 100 years ago.
Wait, you said this device is the only reason we use AC today. Why couldn't we just transmit direct current, DC, using wires?
Excellent question, and this is where the real deep dive begins. When we send electricity over hundreds of kilometers from a power plant, we lose energy as heat, defined by the formula P loss equals I squared R. That I's term, the current, is squared. That makes it highly sensitive to how much current flows. If we were forced to transmit power at a safe home voltage, say 230 volts, the current needed to deliver megawatts of power would be enormous. That huge current would mean gigantic I squared R losses, effectively wasting most of the generated power just heating up the transmission lines. The transformer provides the solution. Use a step-up transformer right at the power station to boost the voltage up to, say, 400,000 volts. Since the power, P equals VI, must remain constant, boosting V makes the current I tiny.
And tiny current means minuscule I squared R losses along the long transmission wires. Then at the city, we use a step-down transformer to bring the voltage back to a safe, usable level. That makes perfect sense for infrastructure planning.
It's elegant physics applied to a massive logistical problem. Now, to anchor this VI trade-off, let us use the best analogy available: the gear system on a bicycle. Imagine shifting to a high gear for maximum speed on a straight road. That action is exactly like a step-up transformer. You apply low force or low current to the pedal, but you get a very high rotational speed or high voltage at the wheel. Conversely, when you shift into a low gear to climb a steep hill, that is a step-down operation. You apply maximum force, high current, but the wheel rotates slowly, which is like a low voltage. In both cases, the total power, your energy expenditure remains the same. You merely traded force for speed.
That analogy helps a lot with the proportional relationship. But if the principle is so simple, why are the transformers in the substation so massive while my phone charger is tiny? Isn't the magnetic principle the same?
That is a very insightful question. The principle is the same, but the power handling capacity is different. And that depends on the heart of the device, the soft iron core. This leads us to our mental image, the magnetic handshake. Imagine the primary coil waving its magnetic field north, south, back and forth continuously because of the AC current. The soft iron core's job is critical. It acts like an efficient closed pipe, capturing virtually all of this magnetic flux and guiding it straight to the secondary coil. The two coils never touch electrically. They communicate purely via this rapidly changing, guided, waving magnetic field. The size and quality of that core determine how much power the transformer can handle efficiently, giving you those massive substation boxes versus a tiny charger adapter. Now that we have the intuition, let us bring in the formality. As you prepare for your syllabus, you need to know how the governing body defines this device and its core mathematical relationships. Could you read what the insert says about the transformer?
Yes, reading the formal definition from the source. A transformer consists of two sets of coils, insulated from each other, wound on a soft iron core. One coil, the primary, has NP turns. The other, the secondary, has Ns turns. It is a device used to change an alternating voltage from one to another of greater or smaller value using the principle of mutual induction.
That is the perfect exam-safe definition. Notice the two key ingredients, AC voltage and mutual induction. Now let us connect this definition to the formula for the transformation ratio. We will do this conceptually, linking it back to Faraday's law. So the entire process starts when the AC voltage, Vp, is applied to the primary coil, which has Np turns. The current it draws creates a magnetic flux, phi, in the iron core. Since the input current is alternating, this magnetic flux is continuously changing with time. This changing flux is contained within the core and links the secondary coil, Ns. Now, Faraday's law of electromagnetic induction dictates that any change in magnetic flux over time induces an EMF. Since the same changing flux passes through both coils, we get an induced EMF in both. Mathematically, the induced voltages are Vp equals minus Npd phi by dt and V equals minus Nsd phi by dt. The critical insight here is that both induced voltages are governed by the exact same rate of flux change, d phi by dt. It is the shared input of the magnetic handshake, you see. Because they share that common term, if we simply divide the second equation by the first one, the common terms cancel out instantly. This leaves us with the transformation ratio. V's over Vp equals N over Np.
So the output voltage is determined purely by the ratio of the number of turns. If the secondary coil has 5 times the number of turns as the primary, the output voltage will be 5 times higher.
Precisely. If Ns is greater than Np, it's step up. If Ns is less than Np, it's step down. Now, we must link this to current because energy is always conserved. Hope everything is clear so far. This concept explainer is from ProfSam.com. That is ProfSam.com. So the law states that for an ideal transformer, power input must equal power output, or VPE equals V as A is. By rearranging this power conservation equation, we confirm the inverse relationship from our bicycle analogy. We find that the current ratio must be inverse to the voltage ratio. IP over is equals V's over V, which equals N's over Np. A voltage goes up, current must come down by the identical ratio. Let us cement this concept with a quick, simple calculation, which is exactly the kind of question you should expect. Suppose we have a step-down transformer serving a small neighborhood. The input voltage Vp is 2200 volts, and the turns ratio, Np to Ns, is 10:1.
Okay, so the secondary voltage V's will be 2200 volts multiplied by the secondary to primary ratio, which is 1 by 10. That gives us 220 volts.
Correct. Now, let's say this transformer is delivering a total output current of 100 amps to the neighborhood. What is the current IP it is drawing from the high voltage line? Remember the inverse ratio.
The turns ratio Ns by Np is 1 by 10, so the current ratio IP by is must also be 1 by 10. So IP is 1/10 of 100 amps. That is, IP equals 10 amps.
Fantastic. You just demonstrated the entire principle. We converted high voltage low, current 2200V, 10A to safe voltage high, current 220V, 100A keeping the power exactly constant at 22,000 watts. This powerful ability, to link changing electricity and changing magnetism, which we call mutual induction, is the practical reason why we studied the entire previous unit on electromagnetic induction. It is the bridge between theory and our entire electrical infrastructure.
That all makes sense for an ideal, perfect scenario. But what about in the real world? What are the tricky edge cases or common misconceptions that people, especially students, fall into?
That is the perfect pivot. Let us tackle the silent killers, those misconceptions that often steal marks because students forget the foundational physics. The first one is believing that transformers can work with a standard DC battery since voltage is voltage. This is the number one blunder. Why is that wrong? Students often forget that the prerequisite for induction is change. A DC battery creates a constant current, which creates a magnetic field that is absolutely constant. If the magnetic field is constant, the rate of change of flux, dy by dt, is zero. Zero rate of change means zero induced EMF in the secondary coil.
So we must always remember, no wiggle, no work. If you don't wiggle the magnetic field with AC, you get no output.
Not only that, but if you connect a real transformer primary coil to DC, the resistance of the winding is usually very low. Since there is no back EMF to oppose the current, the coil draws massive current from the DC source, overheats rapidly, and usually burns out. It becomes an expensive heater. Misconception number 2 is the idea that a step-up transformer increases power because the voltage is higher. This is purely a confusion of terms. We are not a power generator. The law of conservation of energy strictly forbids power creation. Voltage increases, yes, but current decreases proportionally. You cannot increase the total power output. In fact, for any real transformer, P out is always less than P due to inevitable energy losses. And that leads to the final crucial misconception, assuming that all real transformers are nearly 100% efficient, so we don't need to study losses. While good transformers are incredibly efficient, 90 to 99%, the 4 sources of loss are mandatory to mention in an exam.
Can we break down those 4 losses?
Yeah.
I know eddy currents are one, but I often confuse the other 3.
Of course. The first is resistance of windings. Simply I²R loss, as heat is generated when current flows through the copper coils. We use thick copper to minimize this. The second is flux leakage. Despite using the soft iron core, some magnetic field lines escape into the air and fail to link the secondary coil. This is minimized by winding the secondary coil right on top of the primary. The third is eddy currents. These are circulating currents induced in the iron core itself due to the changing magnetic flux. They dissipate energy as heat.
So that's why laminated cores are used. We slice the core into thin, insulated sheets. That insulation prevents the large circulating eddy currents from forming.
Exactly. The lamination dramatically increases the resistance against those currents, cutting down the loss. And finally, the fourth loss is hysteresis. Every time the AC current reverses, the magnetic domains in the core must be repeatedly magnetized and demagnetized. This constant molecular friction requires energy, which is lost as heat.
So, for exams, we must mention that losses occur due to I²R, eddy currents, hysteresis, and flux leakage, even if the transformer is nearly ideal.
Precisely. Okay, let us anchor these core ideas in your memory forever with some powerful hooks. Always remember the catchy phrase, transformers are the gearbox of electricity. They simply trade voltage for current, just like a gearbox trades speed for force. You can even use a quick physical gesture. Use the squat to jump motion, squat down low, that is low voltage, while spreading your arms wide, representing high current, then jump up high voltage, keeping your arms tight to your body for low current. This instantly anchors the proportional trade-off. And finally, a slightly funny association that should make the DC mistake unforgettable. Connect a transformer to DC and it becomes a heater. Connect it to AC and it becomes a magician. That should remind you instantly why AC is essential for the magic of mutual induction. Let us now summarize the essential takeaways in 3 exam-safe factual bullets, consolidating all we've learned. Point 1. A transformer is a static device that uses mutual induction to transform AC voltage levels by creating and coupling a changing magnetic flux. Summary point 2. The voltage transformation ratio is defined strictly by the number of turns in each coil. V's over VP equals N's over NP. If N's is greater than NP, it is a step-up transformer. And finally, summary point 3. For an ideal transformer, energy is conserved, meaning power input equals power output, and the current ratio is inversely related to the voltage ratio. RP over is equals N's over NP. To get maximum marks in 12 CBSE physics, chemistry, and maths, visit ProfSam.com.
That is ProfSam, right?
Yes, correct. ProfSam.com. We thank you for joining this deep dive, and we hope this concept is crystal clear for your exams and beyond. Study well.